General Relativity, Lecture 10. The Friedmann-Robertson-Walker Geometry. In this lecture, we review the basics of the description of our universe. The appropriate geometry goes under the name Friedmann-Robertson-Walker geometry. We actually start similarly to what we did so far. In both cases of Schwarzschild and Kerr metric, we started with considering the symmetry of the problem, and then we deduced the form of the metric. So let us look at the universe. If we look not so far away, then we recognize the Milky Way, which is our galaxy. A little farther there is Andromeda Galaxy, and other smaller galaxies from our local group. Above that, we find ourselves on the outer part of a giant supercluster of galaxies. In the whole universe, we see such superclusters, and we see them from our standpoint isotropic. So the observation is that on small scales we see structures, but on large scales we see the universe as isotropic. The first symmetry is then isotropy. Then there comes a principle which in modern days we take as granted, but which actually cannot be supported by a direct observation. That is, that there is no preferred observer in the universe, or a preferred center of the universe. This goes under the name Copernican principle. Out of these two, the implication is that the universe must be spatially homogeneous. So this is carefully put together in the cosmological principle, which states that at any particular time the universe looks isotropic and the same from any position in space you choose for observation. This now brings a problem, because the principle is formulated so that we refer to some time global for the whole universe, and I also have separated space from the time. But we are in relativity, so they must be coupled, and we know that there is no global inertial frame. So we have to say a little bit more about what is actually meant by the time and space. The idea is the following. The whole universe is filled with some matter or energy, and I use these two words very loosely as synonyma because they are coupled. In today's observation, these are the galaxies and any other matter that fills the universe. There is some local motion on the level of galaxies, for example, they rotate. So I average out all this local motion and arrive to a matter distribution where the matter moves with velocities that differ on large scales, on which the universe is homogeneous, but the differences of velocities on small scales where the universe is not homogeneous are averaged out. So what I have constructed is the model of a cosmological fluid. It flows with velocity differences over large scales, but with averaged out velocities over small scales. With this, we introduce the fundamental observers who locally co-move with the cosmological fluid. In other words, they have zero peculiar velocity. Peculiar velocity is the velocity with respect to the instantaneous rest frame of the fluid. The fundamental observers evolve along time-like world lines. The set of all these world lines is called the congruence. Now, then comes another postulate called the Weil's postulate. The congruence of world lines of all fundamental observers is hypersurface orthogonal. This means that we can construct a three-dimensional space-like hypersurface that is orthogonal to all world lines and assign it a value of the time coordinate which will be common for all the intersecting points at all the world lines. Another hypersurface crosses the congruence at different positions and assumes a different time coordinate. So we have naturally sliced the spacetime into hypersurfaces corresponding to three-dimensional space and which are ordered in time by threading of the world lines of fundamental observers. Based on this, we introduce the synchronous co-moving coordinates. The labels of the spacetime hypersurfaces are taken to be the proper time. And so, we have defined the synchronous time coordinate or the cosmic time. The spatial coordinates are chosen so that the fundamental observers do not change their coordinates, so they are co-moving. Since the hypersurfaces are orthogonal to the world line of fundamental observers, there will be no time-space cross terms in the metric. Now, what can we deduce from homogeneity and isotropy? So, let us look only at the space-like part of the metric tensor. The distance between 2 points is this. The distance may change with time, but the change must not depend on where these 2 points are in space because of the homogeneity. Also, it must not depend on how they are oriented with respect to each other because of the isotropy. And so, the distance can only change due to a time-dependent factor which is common for all components of the metric. So the spacetime metric will be the following. There is no preferred direction in the 3 space, but there may be a curvature. However, it must be the same in all directions. So at every point, there should be just one number that specifies the curvature. Moreover, since we have homogeneity, that number must be common for the whole space. Then if we take all the symmetries and antisymmetries of the Riemann tensor, it must have this form. It is straightforward to calculate the Ricci tensor and also the scalar curvature. Now we want to write down the metric for an isotropic space. We have done this already in lecture 6 when we derived the Schwarzschild metric. So we'll go through this quickly because it is just repeating the arguments. There may be only the rotational invariance in the metric. And so in spherical coordinates, the metric takes this form. And R can be rescaled so that we simplify the form. And we will need to determine the function b. And we do it by matching the curvature. So we have to calculate the curvature from this metric. Here are the connection coefficients, only those which are non-zero. And from them, the Ricci tensor can be calculated. And the non-zero components are only the diagonal ones. This is now put into equation with this. And for the first 2 components of the Ricci tensor, we obtain this. The first equation can be integrated. And here A is the integration constant. And the integration constant can be determined from the second equation. So we calculate the derivative and insert everything into the second equation. And from this we deduce that A equals to 0. So the metric in the 3 space takes this form. It looks like there is a specific point which is the center of this coordinate system. But this can be chosen completely arbitrary, so the requirement of homogeneity is respected. Based on this, we now write down the metric of the whole space-time. Remember that k can have any value. Now, it is customary for non-zero k that the r coordinate is rescaled so that the absolute value of k is absorbed into the new coordinate, which we call r bar for a while. And so the metric is modified. And here the small k is actually the sign of capital K, and it is 0 if capital K is 0. To simplify the writing, we denote the prefactor before the bracket as one function, capital R, which is identical to S if the curvature is 0. And also for simplicity, we finally drop the bars over the R and obtain the line element in the Friedmann-Robertson-Walker metric. These three different choices of K lead to three different geometries of the space-time. Let us start with a positive spatial curvature where K equals to 1. In this case, there is a peculiarity in the metric because the coefficients of dr squared becomes singular as r goes to 1, and it would be negative if r is bigger than 1. But that would change the signature of the metric, and we do not want that. So we rather limit ourselves to the interval from 0 to 1 for r. Remember that r is a radial coordinate. It is not really the distance from the center. So in this case, it is convenient to replace it with a sinus of some angle. And then dr is this. If we only take the spatial part of the metric, then the line element is this. Let us understand what this means. I'm going to claim that this is a specific hypersurface if it is embedded in a four-dimensional Euclidean space. If spherical coordinates are introduced in four-dimensional Euclidean space, then the Cartesian coordinates are expressed like here. If we now keep r constant, so that we specify the hypersurface of a three-sphere, then the differentials are calculated like this. And if this is worked out, then we get the line element on such a hypersurface here, like this. And this is exactly the form that we obtained from the Friedmann-Robertson-Walker metric with k equal to 1. So in this case, r is sometimes referred as the radius of the universe. If we look at the case with k equal to 0, then the three-space element is simple, but to keep our coordinates consistent, we replace r with chi. So the line element is this. And this is simply what we get with spherical coordinates in ordinary three-dimensional Euclidean space. The last possibility is that the spatial curvature is negative. Again, we substitute r, but this time with hyperbolic sinus, and so that we cancel the metric component at dr squared. Then the spatial part of the Friedmann-Robertson-Walker metric is this. Again, I'd like to visualize in quotation marks what kind of space this is. And I'm going to claim that this is a three-dimensional hyperboloid which could be embedded in a four-dimensional Minkowski space. The hyperboloid is defined by this constraint. And the constraint can be satisfied by appropriate parametrization of the hypersurface, which is this. Now the Minkowski space, which we use for embedding, has opposite metric to what we use in this course. you are invited to show that if we calculate this line element on the hypersurface, then we directly obtain the spatial part of the Friedmann-Robertson-Walker metric for k equals to minus 1. We summarize all these cases with a new form of the Friedmann-Robertson-Walker metric. We next look at the geodesics in the Friedmann-Robertson-Walker metric. We will use the geodesic equation in this form. Here we use u, which is the derivative of the coordinate with respect to the affine parameter, and the dot stands for the derivative with respect to the affine parameter. On this equation we see that if the metric does not depend on coordinate x mu, then u mu is conserved. Evidently we need the components of the metric tensor. We will use the last formulation of the metric, and so we summarize them here. Still, before we consider the geodesic equation, we introduce a trick. We place the origin of the coordinate frame to the point in which we consider the geodesic. The good thing is that we can do it because the space is homogeneous. So, now let us look at the individual components of the for velocity. The metric does neither depend on phi nor on theta, and so those components of the velocity will be conserved. Let's start with phi, which is the third component. Since we consider this at the origin, s must be 0. And so therefore, u3 must be 0 and phi stays constant. Similarly, it will work for u2. And so for the same reason, it also must be 0, and the theta coordinate also does not change. The equation for the r component is this. And now the second and third components of the velocity are 0, and so the only possible contributions are these two. However, neither g00 nor g11 depend on r or chi, and so again this velocity must be constant. Now the 0th component we will determine from the normalization condition. For massive particles we must have that u squared is equal to c squared. And for massless particles we have that u squared is equal to 0. Now from this equation for the photons we can derive the formula for the cosmological redshift. So we put this equation into this form. And now if this describes a light pulse which an emitter sends to a receiver, then we can integrate these coordinates along the path of the photon. Now if he sends another light pulse just an infinitesimal delay later, then the boundaries on the left-hand side shift, but those on the right-hand side do not. So this means that the two left-hand sides are equal. And we cancel those parts of the integrals which are there on both sides, and we're left with this. But since the time intervals are infinitesimal, the integrands may be considered constant, and we arrive at this relation. These time shifts may be the delays between two crests of the light wave. In other words, this may be the period at the place of the emitter and the period at the place of the receiver. So we can write this ratio of frequencies. And the redshift z is actually defined in this way. The next feature encoded in the metrics, which we are going to look at, is the time dependence of the scale factor r. This is commonly known through the expansion of the universe. We will denote the present time as t0. If we observe the objects in the universe, we look at signals which were sent out in the past. If the past is not too ancient, then for recent past we can tailor or expand the scale factor r around the present time. The dot here means differentiation with respect to t, and this we still rewrite into the second form, where we introduce the Hubble parameter h and the deceleration parameter q. The usual notation of the present day values is h0 and q0. With this, we can calculate the redshift for a photon emitted in recent past and observed today from this relation. If the look-back time t0 minus t is small, there again we can Taylor expand this expression up to the second order in the time difference and get this. Now the redshift is the observed quantity, while the look-back time is not. And so it is more useful to express the look-back time from the redshift. We can solve this quadratic equation and get this. And obviously only the upper sign applies because we want a positive look-back time. If we say that the redshift is small, then we can Taylor expand up to second order in z, and this is the result. We can also calculate the chi-coordinate of the emitter if we assume that the present observer sits at 0. We use this integral equation, which we derived previously. And for r as a function of t, we use the Taylor expansion. And so here is the integral. We still assume that the look-back time is small, and so we can Taylor expand the integrand. If we want the result of the integral up to second order, then here it is enough to expand up to first order under the integral. But finally, we want to express chi as a function of the redshift. And so we insert for t0 minus t and express it through z. And we go to second order in z. If this is now the coordinate of some galaxy and we sit at 0, then the distance to that galaxy is r0 times chi. If we use the last equation, then we have this. Now we see that if z is really small and we limit ourselves to the first order in z, then we have this. As we would interpret the redshift as being due to Doppler shift due to galaxy receding from us with some velocity v, then the right-hand side is given just by this velocity of the galaxy. This is the Hubble's law discovered in 1929. We now see actually that it is due to the leading term in the Taylor expansion of the scale parameter. We see from this derivation that the Hubble constant is only the constant just now, but otherwise it is a function of time. Recall that it was given by this ratio. Now, to get the first estimate how this function of time looks like, we use the Taylor expansion for r and r dot. And we express the look-back time through the redshift up to first order and get this. Now, If we have the Hubble constant as function of the redshift, we can determine the look-back time and the coordinate of the emission of the observed photon. We realize this, and we can then integrate this relation. And for the coordinate, we use this expression which we derived from the photon geodesic. We performed a substitution and use what we derived for the redshift, and then the integral of this is the following. In this discussion we already mentioned the distance from a galaxy, but that needs some word to explain. Given the metric, we said that the proper distance is this. But this is practically not measurable. So for practical use, we need some operationally defined distances. And these can be luminosity distance and the angular diameter distance. Let's look at the first one. If we have a radiating source, then its absolute luminosity is the total energy radiated per unit time. In Euclidean space, the flux of energy measured at distance d goes down as 1 over d squared. The luminosity distance is based on this relation and depends on the squared root of the ratio L over F. We do not have Euclidean space, however. We have the Friedmann-Robertson-Walker geometry. And so we need to relate this definition to the quantities of the metric. Suppose that the emitter as well as the receiver co-move with the cosmological fluid. So their chi-coordinates are fixed. We put the emitter at 0 and the observer at chi. The photons must be emitted earlier at time t(e) so that they are observed at the time t0. During this time, they spread out isotropically into a sphere with this proper area. But there is another factor which decreases the received energy. Each photon is redshifted by the factor 1 over 1 plus z. This is the observed over the emitted frequency. And by the same factor, also the arrival rate is decreased. So altogether, we have this flux. And so for the luminosity distance, we derive this. The other possibility was the angular diameter distance. Again, the motivation is from the Euclidean space. If we have an object with the proper diameter L far away, and we observe it on the angular diameter delta theta, then the distance is this, L over delta theta. And again, we have to relate it to the coordinates in the Friedmann-Robertson-Walker geometry. Let us sketch the situation. The observer sits at 0, and the observed object sits at some distance chi. Consider two of its points that are situated at the same coordinate phi. The photons from these 2 points arrive at the position of the observer at time t0. During the time as they propagate, they always stay at the same value of phi. They arrive to the observer with the angular distance delta theta. It is the observer who measures the distance, and so we have to consider the measurement from his point of view. So we have to project the world lines of the photons along the world lines of the observer. As you do that, the distance between the observer and the source that counts is the one at the time when the photons were produced. So r is taken at the time te. So then the geometry is such that the size of the emitting object is this. And so the angular diameter distance we would get is this. But we would like to express the scaling factor r with its value at the time of observation, R0. And so we do it with the help of the redshift. Now you can see that there is a difference between the luminosity distance and the angular diameter distance. They differ by the factor 1 plus z squared. The last purely geometrical topics that we look at is the evolution of the volumes and number densities in the Friedmann-Robertson-Walker metric. To be specific, we want to look at the 3 volume. With this metric, the infinitesimal volume, which corresponds to the coordinate interval from chi to chi plus d chi, and solid angle sinus theta d phi, is this. Practically, the distances are often measured with the redshifts, and so we replace d chi by dz. But then we need the derivative. This we obtain from a relation that we derived previously. And so we get for the volume this. This is the present day volume element. But often, when we consider expanding universe, it is useful to derive the time dependence of the volume. To get this, it is easiest to look at the first relation that we had for the volume. It is proportional to R0 to the third power. And the only time dependence in this is in R. So if we know how R is time dependent, then we can plug it in. Now the look back time can also be expressed through the redshift, which we use here. So we'll stick with the redshift and express everything with the redshift. Now we had this relation for the redshift. And so R at any time or any redshift can be expressed as R0 over 1 plus z. So we can use it for the volume. Now this is practically useful, to have the volume as the function of z. Suppose you want to count the galaxies in the sky that you see in solid angle delta omega in some redshift interval from z to z plus dz. This is then the density of galaxies at that redshift times dV. But the second term is the present day volume. So if the galaxies are not destroyed, then nz over 1 plus z to the third power must be the present day density of galaxies. And so we also derive the time evolution of the density. As a consequence, if we want to count all galaxies up to some redshift zf, and we assume that they were not destroyed meanwhile, then we integrate this relation. The angular integral brings 4 pi, and we get this. And to calculate this integral, we must know how r evolved with time. In the last part of this lecture, we sketch up the cosmological field equations, which are the Einstein equations for the Friedmann-Robertson-Walker metric. The goal in solving this equation is to find the time dependence of R. We use the Einstein equation in the form with only the Ricci tensor on the left-hand side. Let's start now with the left-hand side, so we need the Ricci tensor. We go back to the coordinates t, r, theta, and phi, and use the metric in this form. So these are the components of the metric. The next step are the connection coefficients, and the non-zero ones are these. The Ricci tensor components are directly calculated from this formula. It turns out that only the diagonal terms are non-zero. They are here. Now we turn to the right-hand side of the Einstein equations. There is the energy-momentum tensor. We take a simple model and neglect viscosity and heat conduction. So we assume that the energy-momentum tensor is that of perfect fluid. That density and pressure must be functions of only the cosmic time. This is the cosmological fluid, so it co-moves with the coordinates. Then, its contravariant for velocity has only the zeroth component, and similarly the covariant for velocity. So, the energy-momentum tensor is then this, and we easily calculate its contraction. So altogether, the right-hand side of the Einstein's equations is this. If you look at this, the metric tensor is diagonal, so also here we only have diagonal terms. We write them out explicitly. So now we can put the 0, 0 component into equation with the 0, 0 component of the Ricci tensor. And if we look closely at the remaining three components, the three equations would be equivalent. So we cancel the factors on both sides and arrive at this. We insert for kappa. From the first equation, we express r double dot. And in the second equation, we insert for r double dot and express r dot squared. The pressure cancels out and we collect the other terms. The last two framed equations are called the Friedmann-Lemaitre equations. If lambda is set to 0, then they are called Friedmann equations. For the Friedmann equations, there is no solution where r would be constant. So this kills the idea of a static universe and led Einstein to introduce his cosmological constant. We are not going to further discuss the solutions of these equations, but we are going, as the final topic, consider the energy-momentum conservation equation. So, as a reminder, it looks like this. But this can be manipulated into continuity equation, which is this, and the equation of motion for the cosmological fluid. The second equation is actually trivial, because there is 0 on both sides. We can show this. Let's start with the left-hand side. We have there the covariant derivative of velocity multiplied by u mu. The velocity is constant, and so the first term vanishes. As for the second term, the velocities only have zeroth component, and so only gamma with two lower indices equal to 0 contributes. But there is no such Christoffel symbol, which would be non-zero. So also here we get 0. On the right-hand side, we have nabla p, but p is a scalar function, so that this is equal to ordinary derivative. And since p only depends on time, only the zeroth derivative contributes. So the index mu must be 0. Now g mu nu only has diagonal components, and so from the bracket only the 0, 0 component can contribute. But that is 0. So also the right-hand side vanishes. Now let us turn back to the continuity equation. We write out the covariant derivatives. Since rho is scalar, in the first term we can replace covariant derivative with the normal derivative, and since it is multiplied with u mu, it only includes the zeroth component, which is the time derivative. In the second term, the derivative of the velocity is 0. And since the velocity only has zeroth component, which is 1, we get the sum of those gammas with second index 0. They give 3r dot over r. So altogether, we get this equation. We want to get the evolution of rho. We separate the density and the pressure. Now the trick is to multiply this equation with r cubed. We would finally like to see how the density is related to the scale parameter r. To this end, we rewrite the derivative with respect to r. To solve this, we need to know how pressure is related to the density, so we need the equation of state. We assume that it is proportional to the density. The particular choices would be W equal to 0 for dust, W equal to 1/3 for radiation, or W equal to -1 for vacuum with non-zero cosmological constant. To make the differential equation separable, we substitute rho r cubed by a new variable q, and this is then the equation to be solved. So the solution is then this, and if we come back to the density, we arrive at this scaling. If the cosmological fluid has more than one component, which do not interact, then each component evolves like this with its own parameter W. This can be, for example, dust and radiation. Generally, if W is bigger than 0, then there is pressure, and as the volume increases, then work is done. So the energy density of such a component drops faster due to that work. This can change the relative contribution of each component to the total density in the course of time.